Hi, Gil. I thought it might be useful to have another example of hypothesis testing. So we're going to talk through the main ideas and an example. So where it starts is considering two hypotheses, right? And they should be in contrast to each other. The null hypothesis is basically that any difference between our sample and a hypothesized value, something that's expected or predicted or the usual, is just random chance, right? So this will always look like our population parameter. So far, the population proportion P is equal to some other number. The alternative hypothesis, in contrast, says that there's something different going on. P isn't equal to that value. There's some difference. It could be greater than or less than, or we could just say not equal to. But something else is going on. Usually this is the one that suggests something interesting, a biological process or real difference between two groups. So here's an example. Suppose we want to know if more than 30% of donuts sold in a donut shop are glazed. And we won't need this information now, but just for later, we're going to do a test with a 0.1 level of significance. So we need our two hypotheses here. The null hypothesis should look like the population proportion P is equal to some number. Here, right, our best guess, or kind of the expected number for what that percentage should be, is 30%. Or P equals 0.3. Right, but what we want to know, what we're testing, is if it's more than that. Right, so we're comparing P to 0.3, right, and we want to know if P is actually greater than 0.3. So that's our alternative hypothesis. So these are the two things that we think might be going on. It's 30% or it's greater. So this is all kind of the theorizing, what's happening in the whole population. But we can't measure the whole population. We can only measure a sample, right? So we'll take sample data and we'll get some result, the sample proportion, right? How many of the donuts in our sample were actually glazed? What percentage? Once we have that sample data, we can compare that result, our sample proportion, to the null hypothesis. We can see how compatible they are, right? Does our result make sense if the null hypothesis is true? To be a little more precise, what we calculate is how likely it is that if the null hypothesis were true, a result like our sample would occur just by chance. Here's how we do that. We assume the null hypothesis is true, right? So here we'll assume that the true population proportion of sold donuts that are glazed is 30%. And then we'll simulate, but we could also calculate or approximate what would happen if that were true, and if we took many samples of the same size as our actual sample. How many of them would have the same number of glazed donuts, or even more, right? Because we're thinking about greater than 30%. So we want to know kind of how many are extreme in the greater than direction. Right, what do I mean by extreme? I keep using that word. That's basically saying that a sample result is as far away from the null hypothesis as our sample was, or even further. But we only care about that in the direction of the alternative hypothesis. So if our alternative hypothesis had a not equal sign, we would think about distance from the null in both directions, right? But ours was just greater than, so we'll only go in the greater than direction. So in our example, our alternative hypothesis was that P was greater than 0.3. So keep that in mind when we're thinking about what is extreme. So now let's look at our sample data. Let's say we took a sample of 40 donuts that had been sold. We found that 15 of them were glazed. So the first thing we need to know is, what is that sample proportion? So to find that, we divide 15 by 40. So that's our P prime, our sample proportion, and that comes out to 0.375 or 37.5%. So what we're going to calculate, what our p-value is the percentage of samples of size 40 that are at least 37.5% glazed if the true proportion of all donuts sold that are glazed is only 30%. Okay, so remember, our sample data is 15 glazed donuts and 25 unglazed. The hypothesized percent that are glazed is 30%, and we'll take 2,000 samples. That seems like enough. Right, so we have glazed donuts, and there are 15 of them, and unglazed donuts, and there are 25 of them. And I'll say that our variable name is donut type. So let's begin. So we have a graph of the results of our sample and a summary. Now let's go down here to do the simulation. Right, so we want to simulate assuming that the true percent is equal to a hypothesized value, and that hypothesized percent is 30%. And here's where we'll put the samples, 2,000 of them. And we do want glazed to count as successes, right? Those are the ones we're interested in. So let's add our samples. Right, so across many of these samples, we have somewhere around 11 to 13 glazed donuts, right? So 15 is a little on the high side, right? It's right here, but it doesn't look like it's too unusual. Let's find out how weird it is. We'll go greater than or equal to 15. Right, so this is where we're calculating the p-value. We're counting the percent of these 2,000 samples, all of size 40, that had 15 or more glazed donuts. Okay, and this says 438 of those 2,000 samples had at least 15 glazed donuts. So it gives us a probability of 22% of getting a result this extreme if the truth is that about 30% of the donuts are glazed. So this is something that could just happen by random chance. 1 out of every 5 times someone bought 40 donuts. That's pretty often. Right, and that's the number that we call our p-value. So our p-value is 22% or so, or 0.22. To come to a conclusion, now we have to compare our p-value to the level of significance. This was the number I told you to keep in mind at the very beginning, right? We said that this was 0.1, and you'll see this number denoted with the Greek letter alpha, that kind of curvy A. So here's how we make the decision. If our p-value is less than alpha, then that says that a result like the one in our sample is pretty unlikely to happen if the null hypothesis is actually true. So we think that maybe it's not. We reject the null hypothesis, just like saying that it's false, and we'll conclude that there's pretty good evidence for the alternative hypothesis instead. If, however, the p-value is not less than alpha, then a result like ours occurs too often by chance for us to say that the null hypothesis is false. We don't have enough evidence to reject it. And that's what happens here, right? Our p-value was 22% or 0.22, and that's greater than our level of significance of 0.1. So it's entirely possible, based on our sample data, that only 30% of all the donuts sold are glazed. Okay, So we're done with the example, but there are a couple of other things here I want to talk about. One of them is the idea of tails. We'll talk about a one-tailed test and a two-tailed test. This has to do with how we're calculating the probabilities and with our alternative hypothesis. If the alternative hypothesis doesn't guess a direction of difference, if it just says P isn't equal to something, then that's a two-tailed test. And we're thinking about calculating the probability of our results being extreme in both directions. Right? We need to think about a bit of the tail on the right and a bit of the tail on the left. With a one-tailed test like we just did, we only need to think about one of the sides. So ours was like the picture on the left here with the right tail highlighted. But if we had a less than in the alternative hypothesis, it would be like the picture on the right with the left tail highlighted for the p-value. And confidence intervals are really connected to hypothesis tests, but we have to think a little bit carefully about the tails of the tests in order to see that. So let's start with the two-tailed test. It's a little bit easier. If the level of significance is alpha, we'll go back to an example of 0.05 in a second. Then another way to figure out if we reject the null hypothesis or not is to look at a confidence interval with confidence level 1 minus alpha. Right, so with alpha we're 0.05, and we're thinking about a confidence level of 95%. If our alpha, like in our donut example, were 0.1, then we would use a 90% confidence interval. And this is what we were kind of getting at last week. If the null hypothesis is inside the interval, then we can't reject it. Otherwise, we can. So that part isn't too hard. Where it gets tricky is the one-tailed test. Here, we need to use a confidence interval with confidence level 1 minus 2 alpha. Think about subtracting an alpha from both sides. In some sense, confidence intervals are always two-tailed because they're symmetric, right? They reach out the same way in both directions. Here's a picture of that. We'll use alpha equals 0.05 to see it. Let's suppose that somehow we got a sample where the p-value came out to exactly 0.05. We would not reject the null hypothesis there. So to be consistent, our confidence interval should just barely reach out and include the null hypothesis. It should either be the upper bound of the confidence interval or the lower bound. In this picture, where we're doing a right tail test, it's the lower bound, right? The very left of the confidence interval is right at the null hypothesis. They're in the center of our distribution. Okay, so the distance between our sample result and the null hypothesis is exactly the margin of error. So we can kind of think about how big the confidence interval is compared to the distribution by sliding it over, right? So now we've kind of put the center right at the mean of the distribution, right at our hypothesized value. And what we have on either side is an amount of size alpha, right? Which in our example was 5%, 0.05, right? That's what we're using here. So we have 5% on the right, which was actually what we were thinking about for the p-value, but we also have it on the left. Right? That tells us that this confidence interval containing everything else in the distribution, except for those tails, is encompassing 90% of the data. So this kind of shifted over interval is from a 90% confidence interval, right? Even though the level of significance was 0.05, just because the test was one-tailed. We need to think about what's happening to the other tail for the confidence interval. So this might be useful on the project, just to remember these rules. And it's all about the idea that confidence intervals are always symmetric and hypothesis tests aren't necessarily. Have a good weekend, y'all.